Hi. So we're going to be talking about 2.1, and here we're going to be talking about section 2.1 is titled the tangent velocity problems. So we're going to start talking about what a tangent line is. So from geometry, you may recall that a tangent to a circle is a line that intersects the circle at exactly one location. So in the picture here, we see that line T is tangent to the circle at, say, this point P. So the question that we're going to be exploring in section 2.1 is, what does it mean for a line T to be tangent to a curve at some point P? And by curve, we mean like a graph. So let's take a look at an example. So here's some curve C. Here we have some line T that's intersecting P. We ask, is T tangent to the curve C? What do we think? We see that it's tangent T, or that line T is certainly intersecting the curve at one place or at another location. Does that matter? Is it stopping to be a tangent? Now let's contrast that with line L. Now line L only intersects the curve C at one location, but that doesn't really match what we think of when we think of a tangent. So to me, T looks much more like a tangent than L does, because if I just look at the local neighborhood around P, T is behaving very much like the same way the tangent line behaves around the circle, where it looks like it's just intersecting at one point. So what we want to be able to talk about now is we want to be able to write the equation for a line that's tangent to a curve C. So if we're going to call T a tangent, which is what we're going to do, what do we need in order to write the equation for that line T? Well, if you remember back from your algebra class, that was a long time ago, to write the equation for line, we need a point. Well, we got that. We know P, it's got to pass through that. And we would need a slope. How were we going to get a slope from this line T? Well, we're going to start with the slope of a secant line. And now you're probably not remembering from geometry what a secant line is. So remember our example here. The line PQ is a secant line for a circle because it intersects the circle at two places. So let's start or show you how this idea of the slope of a secant line is going to lead us to the slope of the tangent line. And let's do this with a specific example. So let's say we're looking to find the example or find the equation of a tangent line to the parabola y equals x squared at the point 1, 1. So here's my picture. The blue line is like our tangent line, that's what we want. And our pink line is the secant line, that's what we're going to start with. So we're going to start with the slope of our secant line. This is wrong. I have this labeled wrong. The pink line is the tangent, and the blue is the secant. I was looking at that. I was like, that can't be right. Edit. That's what we want. Okay. So if I look at the secant, I have some point Q, x comma x squared. Remember that this is the equation y equals x squared. So if I pick any point to x, its y coordinate necessarily has to be x squared. Now remember, slope is rise over run. So I have the change in y's between p and q over the change in x's, which I've written down here. So remember, that's just the slope, rise over run. I like to think about change in y over change in x. The Greek letter delta represents change. You might remember that from a chemistry class you've had. So, for instance, if we consider the point Q to be x equals 1.5, and y would be then 2.5, remember, y is just x squared, so that's where the 2.25 comes from. The slope there is 2.5. How did I get the point for Q? You got it, right? We picked an x. And then if y is x squared, that'd be 1.5 squared. That's 2.25. Right? Now it's just an arbitrary point. So here's the big idea. This is the big one. This is what we're building towards. This will be what the second half, or this is the big new idea that we're going to be exploring in this next unit. So this is the idea. What if I look at the limit as q gets closer and closer to p of the slope of pq? So go back to our picture here. What if I consider just this point q getting closer and closer and closer to p, and we look at what's happening to the slope? That limit as q approaches p is going to give us the slope of that tangent line at exactly p. It's the instantaneous slope. It's not the slope between 2 points. It's the slope at a single point. So, if we look at this, the slope as q approaches p. The x at q is x, and the x at p is 1. So we want x approaching 1. And we just showed that the slope of the secant line in general for PQ is x squared minus 1 over x minus 1. Right? That was what we did right here. So to evaluate this limit, obviously if I try to do direct substitution, I'm left with 0 over 0, which is indeterminate. But if you look, you'll notice that, hey, x squared minus 1 can factor. That's just a difference of 2 squares. So those reduce. Now I can do a direct substitution. And so the slope of my tangent line is 2. So if we want to write the slope for our tangent line, we know the slope is 2. And my point was the point 1, 1. Remember, that was the point in our example. We're just working back to that. So I'm going to use the point slope equation. So y is 1, m is 2, x is 1. When I say I meant y1 is 1 and x1 is 1. And now I can just distribute the 2 through and add the 1 over, and that would be the slope of my tangent line. So a piece of vocab here, when we talk about the average rate of change, that's going to be talking about the slope of a secant line. When we talk about an instantaneous rate of change, that we're going to be talking about the slope of our tangent line. So, as a little side discussion, calculus, the thing that we're studying right now, is credited to be invented by Isaac Newton. It was actually kind of developed independently between two people, The other person is Gottfried Leibniz. But Newton kind of is the more recognized name. And really what Newton was trying to do is he's trying to describe gravity. His question was, if I have an object that's falling, that hits the ground, I can calculate its average velocity by just taking the distance that it fell and dividing by the elapsed time it took to fall that distance. But what if I wanted the speed or the velocity of the falling object right here? What if I want to know how fast it's going in that instant? That's our instantaneous rate of change. We're talking about finding the slope of a tangent line. This turns into being a big idea that we'll build upon in our next section. But for today, all we want to be working on is getting comfortable with this vocabulary that an average rate of change is just the slope of a secant line, so just the slope between 2 points. An instantaneous rate of change is the slope of a tangent line. That's going to be the limit as x approaches the x-coordinate of our point of the slope of a tangent line in general. Okay, so if we have some function f of x equals x squared plus 2x plus 1, and we want the average from x equals 1 to x equals 2. Well, I know our 1 point is going to be 1 comma 1 squared plus 2 times 1 plus 1, which is 4. And our other point is going to be 2 comma 2 squared plus 2 times 2 plus 1, which is 4, 4, 9. So my average rate of change is going to be the slope of PQ. Just 9 minus 4 over 2 minus 1. Just the slope formula. Rise over run. So that's 5. The instantaneous change, or should I say rate of change, at x equals 1, well, to do that, I have to set up a general secant line. So I know that I have the point 1 comma 4, just because we found out that before. I'm not going to do it again. I'm just going to save myself the effort. And then I have a general point, q, x comma x squared plus 2x plus 1. So what am I going to do? I'm going to take the limit as x approaches 1 of x squared plus 2x plus 1 minus 4 over x minus 1. So again, this is y2. This is y1. This is x2. And this is x1. I'm just using the slope formula. So if I simplify this, I'm going to end up with a limit that we can do. So again, I'm going to factor this. So I get x minus 3 times x plus 1. Oh, shoot. Shucks. I thought I had this worked out to where it was going to work out nicely for us. And now I've boogered it somehow. Anyways, this doesn't work out, but you get the idea of what I'm going to be trying to do here. And that's the gist of it. This is what you're going to be doing in section 2.1. It's just going to be calculating instantaneous rates of change and average rates of change. More often than not, you'll have a story problem with some context associated to it. But that's the gist of it. That's all I want to talk about today. Good luck and have a good weekend.